Look at it. That is a real planet. Confirmed. Photographed, studied, and it is blue. Not orange like Mars. Not beige like Saturn. Blue like Earth from space. Like oceans. Like sky. Like somewhere you could breathe. But that blue is a lie. HD 189733b is 64 light-years away. And every second of every day, it is raining glass at 5,400 miles per hour. And that's not even the strangest part. HD 189733b is a gas giant, a planet with no solid surface, roughly the size of Jupiter, orbiting a star just 64 light-years from Earth. In cosmic terms, that is close, extraordinarily close. The star it orbits, HD 189733, is actually visible to the naked eye on a clear night, near the constellation Vulpecula, the Little Fox. It was discovered in 2005 when astronomers noticed the star dim slightly, rhythmically, the planet passing in front of it. That dimming told us the planet's size. Spectroscopy, the technique of splitting starlight into its component colors, told us what its atmosphere was made of. What they found made this one of the most studied planets outside our solar system. Not because it was promising, because it was terrifying. It is tidally locked. One face forever pointed at its star, one face forever pointed at the dark. And what happens in between is unlike anything in our solar system. The heat alone should be the headline, but it isn't. Let's talk about what actually kills you here. Not heat first, wind first. Estimates from atmospheric models suggest winds on HD 189733b exceed 5,400 miles per hour, roughly 8,700 kilometers per hour. To put that in human terms, the fastest wind ever recorded on Earth hit 253 miles per hour. HD 189733b is more than 20 times that, permanently. It is not a storm system. It is the standard state of the atmosphere. Now add glass. The planet's atmosphere contains silicate particles. Silicates are the same mineral family as the sand on a beach, the glass in a window. At HD 189733b's temperatures, they vaporize in the hot dayside atmosphere, then travel to the cooler regions where evidence suggests they condense into microscopic solid particles, potentially sharp-edged, like fine glass dust. Those particles are then driven by the 5,400 mile per hour wind horizontally across the sky. Not falling, horizontal, sideways, continuously. This is not rain in any sense, you know. This is a planetary scale grinding machine. Every atmospheric layer a different blade. And the color, that beautiful, deceptive blue, comes from exactly this. Here is why HD 189733b is blue. When sunlight hits the silicate particles in its atmosphere, they scatter short wavelength light, blue light, back into space. The same basic principle that makes Earth's sky blue. But here, it is the entire planet. Every angle, every observation, a deep, vivid sapphire, earned through violence. The planet is tidally locked to its star. That means one hemisphere faces the star forever, receiving permanent, unrelenting radiation. Dayside temperatures exceed 1,000 degrees Celsius. That is hot enough to melt copper, hot enough to soften steel. The night side is cooler, but not survivable. And the temperature difference between day and night drives those catastrophic winds. Heat tries to redistribute itself from the hot side to the cold side, and the result is a continuous, planet-wide atmospheric river moving at supersonic speeds. There is no calm, no eye, no weather system. Only weather itself, locked in permanent planetary motion for billions of years. This atmosphere is not a skin, it is a weapon. So what would actually happen if something, or someone, entered it? Let's run the scenario. You are descending toward HD 189733b. Not through the surface, there is no surface to land on. You are entering the atmosphere in a hypothetical craft. The first problem is velocity management. The winds here don't just push, they shear. Different atmospheric layers move at different speeds and potentially different directions. Your craft would be subjected to forces tearing it apart laterally, not just slowing it down from below. Engineering systems designed for the worst atmospheric entry in our solar system Venus, with its 92 atmospheres of pressure, would face entirely different failure modes here. Assume, hypothetically, your craft survives entry. Now you are suspended in the upper atmosphere. The temperature is over 1,000 degrees Celsius on the day side. The silicate particles aren't visible. They're micron scale. You wouldn't see the glass coming. You'd feel pressure, then heat, then the abrasive effect of continuous particulate impact at supersonic velocity. The Venera 13 lander, the toughest atmospheric probe ever built, survived 127 minutes on Venus. Models suggest that benchmark would not apply here. What kills you first is the wind, not because it blows you away, because it turns the air itself into a medium of erosion. You wouldn't experience the planet. The planet would experience you, and yet we are deeply grateful it exists. HD 189733b is not a curiosity. It is a cornerstone. It was one of the first exoplanets to have its actual color directly measured. Not inferred, not modeled, but observed. That achievement validated an entire family of observational techniques now used across hundreds of planetary systems. Every time an astronomer characterizes the atmosphere of a distant world, the methodology traces back in part to what we learned here. The silicate clouds, the wind dynamics, the heat redistribution between a tidally locked day and night side. These are not edge cases. Evidence suggests this pattern may be common among hot Jupiters, a class of planets that appear throughout the galaxy. Understanding HD 189733b tells us how planetary atmospheres work under extreme stress, and that matters for Earth. Every extreme world we understand is one more data point in the question of what makes a planet livable. You learn survival by studying death. HD 189733b is 64 light-years away, and it is one of the most scientifically productive objects we have ever found. But there is one more thing about this planet, and it changes how you see it entirely. Here is the twist. By some older definitions of the term, HD 189733b orbits within what was once loosely called a habitable zone, a region where conditions could, under the right circumstances, allow for liquid water. That definition has since been refined, significantly, but the point stands. Blue planet, close orbit, the right distance. On paper, it looked promising. The universe presented us with something that looked like home. And then the data came in. HD 189733b is proof that appearance is not evidence. That color is not safety. That the universe will build something beautiful and fill it with glass. And it is 64 light-years away, which means the light reaching your eyes right now left that planet when you were a child. Next time we go somewhere hotter, somewhere that makes HD 189733b look like a mild afternoon. KELT 9b, a planet hotter than most stars. That story is next.